All right, I'm talking about GAM, which stands for Geometric Associative Memory, and this is a key component in what we have. So the general idea is that we want to be able to understand complex or very large knowledge graphs. So the example I'll be working with is the WorldNet dataset. In this, each of the vertices correspond to English words, and they're connected if they're related in some way, be it a hypernym, homonym, what have you. So rather than tackling the entire knowledge graph by itself, what we do is we identify regions of interest and take a neighborhood of that region and embed it in a hyperbolic three-manifold. All right, so here's what I mean by that. If we looked up so I've pre-calculated various regions, various cycles. The first one is filtrate, or has to do with the word filtrate, percolate, percolation, etc. We could look at another one, which comes out, this looks like, hey, deception, trickery, flim-flam, what have you. And then I could draw the picture that is generated by this. So let's pick a few components and take a look at what the neighborhood of that region in our overall graph looks like. So here is a subgraph of our big graph where we have our prankster flim-flam part over here on the left, and then over on the right we have percolate, infiltrate, etc. And maybe we have some sequence that connects them. So this picture is showing a specific region or a specific component of the overall graph that we're trying to understand. If we want to do some sort of link completion or what have you task, we're going to take this and we're going to embed it in a hyperbolic three-manifold. All right, so here's the second piece of that. What do we mean by hyperbolic three-manifold? Well, a good example of one of these somewhat unusual spaces would be a hall of mirrors. So what we have here is actually a cube, but if we have mirrors on all of the faces in this room that we're in, what we see is a bunch of copies of ourselves sort of spread out to infinity. So we can build out this three-dimensional space by working with some sort of shape and adding in some extra rule. Okay. The space that we will work with for this example is this particular manifold, M116, completely arbitrarily chosen, but we can take a look at what this looks like. Well, if we take this particular shape, which is, kind of a complex shape, and add in the rules that we're gluing green face to green face, blue face to blue face, etc., then we will get a hall of mirrors type effect. So the key piece that what we're doing is we're saying that rather than taking our original graph, our original spine, and just putting it in normal three-dimensional space, we're custom building a hyperbolic three-manifold that's going to, where the structure of this manifold is going to reflect the structure of this graph itself. So here's what that might look like. We can embed the spine. And what it's going to do is it's going to take this particular spine and put it into the space that we had here. And by doing so, it's going to untangle a lot of the complexity. So rather than having the complexity of the graph be reflected by cycles in the graph, the complexity, a lot of it comes from just the fundamental structure of this manifold to begin with. All right. So what this looks like is again going to be a hall of mirrors type effect. We're going to see a bunch of copies of a relatively simple graph. So make this hyperbolic. And this is always best with a black background. Let's go with that. All right, so what we have here in orange is that graph, which looks much simpler than the spine that we started with. The red and then blue components are the Hall of Mirrors further pictures that we would see. Red is one step further, blue is two steps further. But the general idea is that this is a somewhat complicated hyperbolic three-manifold that encompasses the information that we're interested in, that we happen to be interested in. So if we have some question about a knowledge graph, we can focus on a particular region and custom build an object to understand it.